So today we're going to look a bit how to defend from an attacker armed with a mathematician. I know it's after lunch, so yeah. So quickly a few information about myself. I'm Antonio Sanso. I'm a senior software engineer and security researcher working for Adobe Basel. I kind of like to break stuff, so you can find myself listed in some security hall of fame like Google, Facebook, GitHub, Microsoft, PayPal, many others. I kind of break other fun vulnerabilities in some common software like OpenSSL, Google Chrome, Apple Safari. We're going to see one of these today. Little things, I'm a co-author of this a book from Mannings. It's printed this week. It's called Out in Action. And yeah, I'm kind of obsessed with prime numbers, and this kind of helped me find this vulnerability we're going to look into today. Little notion. So it's after lunch. You can really take a nap, fall asleep. If you want to wake up, look for that red star. It's a good time. So I mark the important slides with the red star. The other you can chill out. I don't get offended. The main topic of today is the best protocol ever designed that goes under the name of TLS, or Transport Layer Security. So you kind of use every day. I'm pretty convinced about it. So even when you go to the boxed website, when you see a lock and you see HTTPS, then you're using TLS under the hood. And yeah, how does actually work TLS? I mean, we're not going to go into details, of course, but so this is like a high picture of how it works. So it uses something called hybrid encryption because it uses a mix of symmetric and symmetric encryption. So the first part, your browser and the server, they agree on a shared key, and they do this using asymmetric encryption like RSA or Diffie-Hellman. Then they have this key, and they use this key to encrypt the data between the client and the server. And they do this with symmetric encryption like AES. You might wonder why is hybrid. The reason is pretty simple. Symmetric encryption is much faster, and so they use this as soon as they can. And yeah, this is kind of how it looks like a negotiated connection between a browser and the server. We're going to explore this a bit better. So this is easy. TLS, the Diffie-Hellman ephemeral for key exchange, and then use AES, Galois counter mode for encryption, and some other stuff for PRF. So for today, we're not going to look into this everything, of course. We just focus on this part. This is the really cool part. The other is kind of boring, even for me. Yeah. So which one are the actors we're going to look into today? There is the client, that usually is a browser, the server, and today the vulnerability is going to be about OpenSSL. Then we see the handshake, how it happens. Then there is an attacker, that's me, and some mathematician. Good. So this is a really good moment to leave the room. Again, don't get offended, because after this, some math is going to be shown. So you have been warned. So some math ahead. What do we need to know for today's talk? So really complicated stuff. Addition. I think so far so good. Elementary school, we all did it. Same for multiplication. And now things start to be really tough. We have exponentiation. So high school, I think we're still fine. The last things, this is easy. We're all programmers, and modular is easy. I mean, modular arithmetic is for us is easy peasy. So that's it. All we need to understand today is this for operation, and we can do Diffie-Hellman. So quick hint about public cryptography. It's been introduced in a really great paper for Diffie-Hellman in the 70s, and it's really great paper even now. After so many years, it's still a really actual paper. So if you didn't do a read, you're interested about the topic, still a good one. And in this paper, they introduce a kind of concept of one-way function to be used in cryptography. And what is a one-way function? A one-way function is really easy to describe. It's a function that is easy to be calculated in one direction and really hard to do the opposite. So the one that we'll explore today is the discrete log function. So the easy part is the modular exponentiation. It's really easy to do modular exponentiation. There's no problem. I mean, all you need is is a p, usually prime numbers, a generator, and it's really, for example, if you have a prime number 17 and generator is equal to 3, it's actually really easy to do this operation, like 3 to the 4 mod 17 is pretty easy. Anyone wants to tell the results of this? I give a book. I don't have it yet, sorry. But okay. It's, it's a 13. So it's why this? 3 to the 4 is 81. Mod 17 is pretty easy to understand, this 13. So a computer does this really quick, not only with 17, but with really big numbers, like in cryptography, the numbers that we're going to use are really big. We're going to see an example later on, but are a monster. So of course for 17 it's easy to calculate, but this works and scales well even with extreme big numbers. But the opposite is not the same. It's actually really, really complicated to... computers cannot scale. I mean, they can calculate discrete log for small numbers, but you have the numbers of magnitude we use in cryptography. There's no way at the moment that you can calculate discrete log. A trivial algorithm that we're going to show today is really the normal brute force algorithm to try the solution. But even the most efficient solution to find discrete log, they're not efficient. There is no way to find discrete log of big numbers. Again, here we're going to see trial error algorithm and see how is what means discrete log. But again, of course, the most efficient algorithm, they're not as trivial, but they're still not efficient. So we're going to look for a number where the result is the y is 10. So we do trial error. We try first with x equal to 0. So 3 to the 0 is equal 1. Mod 17 is 1. We're looking for 10. It's no good. So we try with 1. 3 to the 1 is equal 3. So it's not good. Sorry. We try 1. 3 to the 1 is equal 3. We're looking for 10. It's still not good. So we try with 2. 3 to the 2 is equals 9. Mod 17 is still 9. We're not good. And then finally, it looks like we found the right one. So 3 to the 3 is 27. Mod 17, 10. So it looks we found a good one. So again, this is a trial error algorithm. But of course, it works good for 17. But the number that are using cryptography, they kind of look like this. So with 17, it was easy to find all the combination of numbers from 0 to 16, worst case. But when the number you are looking for are this, well, then there's no chance a computer can scale at this magnitude. So that's why it's really complicated, the reverse of the function. Another hint of how the discrete logarithm behaves is this. On the left side, there is the normal analogic logarithm, the one we studied at high school. If you see the plot, the graph, it's really easy, it's really smooth, it's really nice. When you go to the field, the more arithmetic, you see that it's much more scattered, much more unpredictable. That's why it's so complicated to calculate. It's not, there's a lot of unpredictability. Now you're saying, why you're telling me all this? The reason is, believe me or not, whenever you connect to the internet and use HTTPS, your browser and the server, they actually do this kind of math. They do this, they exchange numbers, they agree on a key. It really happens. And how? So basically, when you use Diffie-Hellman for key handshake, when your browser connects to the server picks a random number b, and that's the exponentiation. So that's the normal exponentiation we have seen before. So that's g to the b mod p, and send this to the network. Now, in theory, they should choose this value of b every time different. So this should be every time a different number. That's why here there is this e. So this means Diffie-Hellman ephemeral, because this number should be all the time different. And then the same for the client. So the browser chooses another number, use the p and the x that the server sent, and then send ya to the server. And then they can agree on a shared pre-master key. So basically, the client has a final number that is g to the ab mod p, and the server has a number is g ba mod p. So they're the same number. An adversary that is in the middle that observe whatever it goes on the network, they cannot do the same, because as we said, the discrete log of this function, so just observing ya, yb, there's no way you can calculate a and b. So far so good. You say, I mean, this really works, it's really math that it cannot be broken so far. 2017, there's no one that can break this. But so what is this vulnerability that I hinted at the beginning? Basically, a few months ago, I had the luck to find this in OpenSSL. That basically is a high vulnerability that affected many instances of OpenSSL, and I was able to recover many private keys without using any single line of software mistake in terms of like memory corruption. But I used pure math, and here we're going to see a bit of the details. Some months later, we discovered actually with this researcher from University of Pennsylvania in Michigan that the problem was a bit more spread than OpenSSL, but many people were doing the same mistakes, and many instances were at risk. And again, this kind of vulnerability does not use any classical buffer or flow vulnerability, but it is really based on pure math. And here we're going to see a few of the details. So basically, OpenSSL did 3 little mistakes that combined together, they were done in a way that I could recover this private key. So the first mistake that OpenSSL did is to cache this value of b. So basically, the value of b that was supposed to be ephemeral, it was not anymore, was actually chosen all the time the same. The percent is not a problem. This is just one of the 3 requirements we needed in order to recover this private key, but we had it. The reason is because OpenSSL shipped without using this by default this SSL single DHUs. So basically, they were caching this value of b. First requirement. Second requirement for the attack to succeed is the fact that OpenSSL was not doing any validation. Whatever value the attacker, so it should be the browser, but in this case was me, the attacker was sending to an OpenSSL instance, they were accepting it, doing the classical Diffie-Hellman exponentiation, and encrypted the key with the value that I was actually driving. So that even if I were sending them some kind of invalid value, mathematical invalid value, they didn't care. They went ahead. In order to describe the third things I need to exploit, I need to open a parenthesis. As I said, the server is sending some prime numbers to the client, so to the browser. But which one is a good value for these prime numbers? Which prime numbers should I use? There are so many. Prime numbers are infinite. So which one they should use? There are some guidance. It turns out there are a lot of people. They put some guidance, and they brought some RFC through the IETF umbrella usually, where they put this prime number to use. Before to talk about this, let's open a parenthesis. So p minus 1 is always even, because p is a prime number, so it's odd. So p minus 1 is always an even number. And said that, a good choice for a p to use in this Diffie-Hellman is to use a safe prime. So many RFCs, they actually use this safe prime. And what does mean a safe prime? And it's a prime there, when you do p minus 1 split 2, is still a prime numbers. So this, if you're doing Diffie-Hellman, and you're using a safe prime, you're pretty much doing well. And many RFC, they actually say, don't come with your prime numbers. Here is a safe prime, you can use it. But if you don't want to use a safe prime, and you don't do validation, you better use a kind of prime numbers where the p minus 1 split 2 is not a product of small primes. This is something is important. So if you don't want to use a safe prime, you should at least follow this guidance. Now, why I'm telling you this? Well, it turns out that I was kind of seeing these kind of specifications when I kind of hit this RFC 5114. And yeah, it kind of looked weird to me. I mean, I was looking at these prime numbers, and when I was calculating this p minus 1 split 2, it was done like this. So it was like 2, 3, 5, 4, 3. I mean, they didn't look really small to me. Kind of weird, right? So I went ahead. This made me kind of curious. I said, why? I mean, why there are people suggesting these numbers? Now, before to go ahead, I want to finish the loop, and I'll try to give some answer at the end. I don't have it yet, why they're using this number. But basically now I had all the steps needed to go ahead with this attack. So basically OpenSSL was repeating numbers, OpenSSL was not validating, and OpenSSL was actually introduced this support for RFC 5114. So I could carry out and do this attack. And how did I do it? Basically, I was passing this I could not go into details. I would be open for question, even for coffees, if anyone is into math. But basically, I was calculating this secret number, so the part of the number that was supposed not to leave the server, but I could actually calculate small, piece by piece, this number doing the number mod 2 with 2 operations, the number mod 3 with 3 requests, and so on. Then I use the Chan-Instrument theorem, and again, it's out of this. It's not complicated, but doesn't fit in this talk. And then I could recover completely the secret number of the server. Now, coming back to this RFC 5114. Again, I was kind of really curious. I mean, why I had these numbers? And the more I was looking into this in the internet, the more kind of found weird quoting. I mean, this was an IETF specification. I tried to do an IETF specification in the hot world. It took these 2 years, it's still not actually done. This specification went through in 4 weeks, and it was kind of done by a contractor of the defense, United Kingdom Defense. Now, again, it's only speculation, but kind of found it kind of weird. And basically, that's the story I want to tell you today. And I'm open for question now, or if you don't have anything to ask now, I'm always be open for question afterwards.
So what was the motivation for actually including the option to reuse the value in the first place?
Speed. So they were caching, so speed. They skipped the fact that they had to do an extra exponentiation because they had already the exponentiation done. So the point is, like, it's costly, but not so costly. But they were still caching it. So this is many times the answer why there's this security issues, because people are looking for speed and they forget that it might be kind of dangerous. The interesting part is that only reusing these values per se alone is not a problem. In order to this attack to be carried on, we need all these 3 steps. Interestingly enough, OpenSSL had it, all the 3 steps.
Other question? Okay.
Thank you for the talk.
Welcome.
I'm curious, what do you actually do? Is your job at Adobe this kind of cryptographic research, or what is it actually?
Yeah, I'm a security researcher, so I'm really into. So I do a mix of research. So obviously I do crypto, I do web app research as well. So, and some part of the coding I do is related to an Adobe product that is called AM or CQ5. So I'm responsible. I'm the security team in this product, and yeah, as part of my job is a bit of coding, a bit of research, cryptographic, and web app. And hope it answers your question. I think there's a question there as well.
So were all these 3 issues fixed in OpenSSL? Or did they sufficiently address the issue in your opinion?
Yeah. This was, if you see here, it's a CVE. So it was fixed in last year in January. But now, you know, the issue per se was fixed in January, but this research paper is presented as well next week. So I was lucky enough to work with this researcher, and our paper was accepted to this conference called MDSS as a research conference, crypto conference in the United States. So we're going to show this work as well now. But yeah, OpenSSL fixed, and there's a CV numbers. Was a high vulnerability last year in OpenSSL, 2016. I hope that people fix it for now, but you never know.
What question?
I haven't actually looked at the code, but I've heard that the code of OpenSSL is quite cryptic.
Yeah.
In your opinion, how does that add to or contribute to security problems?
So in this one, maybe not much, because as you see, it's not a memory corruption issue. But yeah, the problem with OpenSSL, the code base is pretty old. So people now are after Heartbleed. Heartbleed was really a point of turn for OpenSSL. They start to take these things more seriously. But the point is, they have a huge code base to clean. So they're doing better. They have even new process and so on, but the code is whatever it is. And C doesn't forgive. That's the point. C is not a language that forgives. The minimal mistakes, you're screwed. Again, in this case, it's more a nerdy crypto issue rather than memory or Heartbleed style. But still, I mean, the point, again, even cryptography doesn't forgive. You do one little mistake and many people, of course, we're all programmers and we are not all interested in, I'm obsessed with these prime numbers, so on, so, but the average programmer is not, and I understand it, it's not into this, right? And it's really easy to do the things wrong.
Okay, time is up. Thank you very much, Antonio.
Thanks a lot.